Hello everyone, I'm Chen. Today I'll be presenting my work, Learning Audiovisual Dereverberation, in collaboration with Wilson, David Howarth, and Kristen Grumman. We see and hear things every second of our lives. The sound we hear is not only the sound emitted from the source, but also the reverberation in the environment. It's the audio signals reflecting off surfaces and objects. It's a function of the room geometry, materials, and speaker locations. It severely degrades human perception and damages speech recognition. Thus, people perform dereverberation to restore the clean speech and has many applications in automatic speech recognition, video conferencing, and AR. Reverberation is a function of the acoustic environment, and here is one example of how one drum kit sounds differently in 5 different spaces. Notice how the geometry or the volume of the room and the material, the surfaces change the sound we hear. Previously, people only used audio to perform dereverberation. In this project, we propose a novel task to leverage the visual acoustic information. More specifically, given an audio and a panoramic view of the environment, the model is tasked to use both the audio and visual information to perform dereverberation. Obtaining the right data for this task is challenging because video data does not contain clean anechoic signal, and recorded impulse response datasets typically don't have camera at mic locations or speaker. Here we introduce both simulated and real data. We want the ability to control environment settings, for example, source receiver locations, the speech of the content of the speech, and the room configurations. So we use the audiovisual simulator sound spaces and the Matterport 3D environment. We use libre speech as the source speech corpus. We simulate speaker appearance with 3D human models. We also render both panorama and normal field of view images. We collect real data in various environments, such as atrium, auditorium, classroom, meeting room, and also various speaker distance. We also record ambient sound of people walking, talking, and etc. To solve this task, we propose a novel model called visually informed dereverberation of audio, or short as VIDA. So we first convert the input speech to a spectrogram and use overlapping sliding window to obtain 2.5 second segments, which is the input audio to the model. Our model then consists of a visual acoustic network and a dereverberation network. The goal of visual acoustic network is to extract room acoustics features from visual inputs. So given RGBD images, we use 2 separate ResNet 18 networks to extract features of both images and then fuse them together. The goal of dereverberation network is to remove reverberation in the input spectrogram conditioned on the visual feature. So given the spectrogram, we use a UNet encoder to extract the audio feature, tau and concatenate with the visual feature, and then use a UNet decoder to predict the clean spectrogram. During training, we first minimize the loss on the magnitude spectrum with the L2 loss. We then, to address the issue of phase wraparound, we map the phase angle to rectangular coordinates and then compute MSE for the phase. Lastly, we propose a novel reverb visual matching loss to enforce the consistency between visual acoustic information and the reverberation in the audio, for which we use the triplet loss, where the anchor is the visual, the positive is the audio feature of the same sample, and the negative is the audio feature from a different sample. We evaluate our model on various downstream tasks, including speech enhancement measured by PSQ, automatic speech recognition measured by WER, and speaker verification measured by EER. We show that we compare against various audio-only baselines, and we show that VIDA outperforms all baselines and ablations. Compare with normal field of view, panorama images leads to better results due to more information in the image. Reverb visual matching laws also help the model to learn a better feature representation. We also see that removing the human mesh in the rendering leads to a performance drop, indicating that the model is reasoning the speaker location for dereverberation. Here we show the results on the real data, and we show that VIDA still outperforms baselines on ASR and SV tasks, showing that our model trained on simulation generalizes to the real world. Here we show two T-SNE visualizations. In the first one, we project the audio embeddings onto a 2D space and color them with the distance to the speaker, and there's a nice transition from yellow to blue. We then project the visual features onto a 2D space and color them with the reverberation time decayed by 60 dB, showing that the visual features capture the acoustic information of the environment. Here are two qualitative examples. The first one is on sound spaces.
As the chase drives away, Mary stands bewildered and perplexed on the doorstep. As the chase drives away, Mary stands bewildered and perplexed on the doorstep. As the chase drives away, Mary stands bewildered and perplexed on the doorstep.
The departure was not at all agreeable. The departure was not at all agreeable. The departure was not at all agreeable.
Thank you for listening.